Hi everyone, my name is Ramy Shahin from University of Toronto, and I'll be presenting my new ideas paper towards Modal Software Engineering. I'll start with an example. Let's assume we have a program, P, that takes three arguments, x, y, and z, and calculates some value. The same program, P, can be applied to multiple sets of inputs, which we call in this paper multiple worlds. This is sometimes referred to as single program multiple data, and this has been implemented in many MapReduce systems, for example. Let's assume that we have these concrete values for x, y, and z. We can see that there is an overlap between those three worlds, as we call them. And because of these overlaps in input, there's also a chance that program state for the three computations is going to be overlapping as well. And the same for the output. If we were to apply any existing MapReduce system to this example here, the first step will be to prepare three input vectors for P and pass them either one by one or in parallel to the function. If P happens to internally call other subroutines or subfunctions Q and R, then it passes values to those accordingly. As we can see in this example, P is gonna call R, passing the value of Z to it, but in all three input vectors, the value of Z is 7. And one question that we're trying to answer in this line of work is, can we call R once instead of 3 times? In this particular example, the notion of overlapping worlds is common in software engineering research. I'm giving 2 examples here, but I think there are also others. So first of all, reasoning about software product lines is an example of the need to reason about multiple worlds. Each world in this case is a product variant. And in the case of product lines, the number of worlds grows exponentially with the number of product line features. So in most practical cases, it's not even possible to enumerate all product variants and reason about each of them individually. The second example is software repositories, where we need to reason about successive versions of software artifacts stored in a repository. And in most cases, again, the delta between 2 successive versions is relatively small with respect to the actual size of the artifacts stored. Again, it's going to be a lot of waste of computational resources to do the reasoning on each of the versions separately. In the case of product lines, we use feature expressions as modalities for values belonging to different sets of products. So to take an example, assume we have a product line with 2 optional features, A and B, then we can have 4 possible product variants, each with a feature expression defining it. So product A and B is the product where we have both features A and B, and not B is the product where we have feature A, but we don't have feature B. Similarly for not A and B, and for not A and not B, neither of the 2 features is present. A variable X can have different values in different product variants. So in this example, X has the value of 3 whenever the feature A is present, which means it has the value of 3 in 2 variants, and value of 5 in the other 2. While variable Y has the value of 2 only in 1 product variant, specifically the one with both features A and B present, and the value of 0 in the rest of the product variants. If we were to add X and Y, then we're adding each row in this table. And again, because we're using feature expressions, then we can compact this result into 3 with feature expression A and not B, and 5 in all the other products. Similarly, version modalities can be used to label values belonging to different versions in software repositories. So assume a repository with 3 versions, v1, v2, and v3. Then again, we have 3 variants, each with the version label. And if x has the value of 3, v1 means that at version 1, it has the value of 3, and its value stays 3 in v2 and becomes 5 in v3. While variable y has the value of 2 in v1, this value turns to 0 in v2 and stays 0 in v3. Again, like in the previous slide, we can add those 2 variables. Going back to our example of program P, again, P is internally calling Q on R, and the naive approach is to generate 3 input vectors and pass them one by one to P, and subsequently P passes the appropriate values to Q and R. What we want to do, on the other hand, is instead of using P, use a program P prime that takes modal values instead of separate input vectors. And in this particular case, as you can see here, P prime is passing only single value 7 to R prime. So it's saving the redundancy that we saw before. And the big research question we're trying to answer is, can we automatically transform P to P prime? And of course, in the general case, can we automatically transform a program written in the language to a semantically equivalent model program? We did that for data log programs, and our results are published in an FSE 19 paper. And we also did it for a Turing-complete subset of Haskell, and our results are published in an UPSLA 20 paper. There are many other application domains to model computing. So, for example, we can use probabilities as modalities. So if we have a probabilistic variable x with the value of 4 in 50% of the worlds and the value of 7 in the other 50%, then we can represent it this way. Y, on the other hand, in this example, has the value of 3 in 30% of the world, 9 in 35%, and 11 in the remaining 35%. With probabilities, we're not explicitly enumerating worlds, but instead quantitatively reasoning about them. So as I said, we know that x will have the value of 4 in 50% of the worlds, but we don't know exactly which 50%, and we actually don't care. As we saw before, we can apply functions to probabilistic variables represented this way, and this is an example of addition. Another example is approximate computing, where we compute over ranges instead of precise values. So in this example, x has the value of the closed interval 5 to 6, y has the value of the closed interval 6 to 8, and as we saw before, we can add them this way. What I presented so far is just scratching the surface of applying modalities to computing. We did some of this work on software product lines, but we want to apply this to at least other domains like software repositories or probabilistic computation. One problem specific to probabilistic computation is how to handle dependent variables. Also, in order to be able to do efficient model computation, we need efficient variation data structures, and this is a research area by itself. Studying the theoretical foundations of model logics and how they relate to programming languages is also one possible research direction. And last but not least, whether we can apply some of the ideas presented here to existing SPMD or MapReduce systems. Thank you so much for listening, and I'll be happy to take your questions.
Hello, I am here now with Ramy Shahin, that just presented work towards modal software engineering, and he would be happy to answer your question. Please write them in the chat. And we have only 5 minutes before the session ends, but then you can join Ramy in the discussion room if you want to continue further. Maybe for people to write. So, meanwhile, while Ramy, you expand a little bit about why we should be interested in this modal software engineering. I mean, the parallel is really fascinating. I like it a lot. Why is it useful then in practice? Why a developer should be interested in this?
So this work was mostly inspired by the analysis of software product lines. This is actually my primary area of research, and the fact that we're reasoning about multiple worlds at the same time is not specific to product lines. So another example in the domain of software engineering research is mining software repositories, where you're doing some kind of analysis on multiple versions of a software system. And the idea is those versions of software or products, in the case of product lines, are intersecting. So if you analyze each instance by itself, this is going to involve lots of redundancy and will be extremely slow. And especially in the case of product lines, it's interactable in most cases. So the idea is how to leverage the commonality between those intersecting worlds and take an existing program that expects reasoning about reasoning about a single world, and so that it can do the same thing for those intersecting worlds at the same time.
And it can scale up to handle large program, because the example you show are little small now for giving the idea.
So the example in the paper is very small. I totally agree. What we actually tried empirically is the analysis of product lines, and we had a couple of papers on that. And we actually saw very promising scalability results. The point is how to generalize this beyond product lines, and this is the idea behind this new paper. It's kind of a phenomena that exists in lots of different application domains, and generalizing beyond product lines is the actual goal.
Okay. We have still 1 minute, not much, for maybe answering one last question. No question from the chat. You also elaborated on future direction of work, so I think it's all clear. I find it is a visionary work for NEAR that we discussed yesterday in the panel. So
yes, I attended the panel yesterday. Yeah, I enjoyed it a lot.
So thank you, Ramy, and we can greet here the audience, and good luck for work, your PhD and everything. Okay.
Thank you so much, Antonio. Thank you.
Thank you. Bye-bye. Bye.
Bye.
Bye.